Okay, now let's start to talk about the conservation of mass in control volume. So before we talk about the equation, we need to introduce an idea of controlled volume. Okay, control volume means the volume, the space of interest. Okay, so any particular problems, you can define a space of interest, right? For example, in this pipe flow problem, like this is an expansion. Okay, so obviously for this problem, the controlled volume is very easy to define. That's a portion of the pipe in red, right? Sometimes is problem dependent. So it's depend on the problem and depend on the engineer who look at the problem, how to study it, okay, and depend on the experience of the engineer. So to define a better control volume. For example, if you have a airplane, a flying airplane, you want to study the fluid around the airplane. So you don't want to define a fixed space because then the airplane passes the space and it disappears. So you want to define a control volume that follows airplanes. So it just give you example. It's problem dependent. Okay, but you have to define a space of interest. Okay, the space you want to study the fluid mechanics. So that's called controlled volume, CV. Okay, so this is the general equation. Okay, it's it look like the derivative and the integration there. Okay, let's look at it one by one, each terms. First one is dm sys dt. That means the total mass, the change of the total mass in the system in terms of time, d over dt, right? Time derivative. So the time rate of change of the mass in the system. But you know, as we define in the first class, we define the system is a quantity of mass. So in a certain system, the mass won't change. So dm system over dt should be equal to 0, right? It doesn't change. So dm system over dt equals d over dt, the integration of rho dv in the control volume. What does that mean? That's the total mass in the control volume. So this term means the time rate of change of mass in the control volume. Okay. And the last term is integration CS on CS rho v dA. V here is velocity. Remember, what is rho v dA? That's the mass flow rate. Okay. So the mass flow rate through the control surface. You integrate it through the control surface. Okay, what means control surface? So look at this diagram again. The whole area in red is control volume, right? Whole entire volume in red is control volume. Okay, the red line, the surface enclosed the control volume, is called controlled surface. Okay, so in this problem, the pipe wall is the control surfaces, and the inlet and the outlet cross sections are also control surfaces. So all the entire surfaces enclose the control volume. It's called control surfaces. So this is the conservation mass equation. The time rate of change of the total mass in the control volume plus the rate of change of the mass in and out the surfaces equals 0. Okay. The reason we have the integration sign here is for the control surfaces is the velocity might not be uniform. The velocity changes on the control surfaces. Could be a non-uniform velocity. Okay, so if that's the case, we need to take integration rho v dA to calculate the mass flow rate, just like we mentioned in the last class. Okay. This is the general equation, general form. But if we make some assumptions, okay, so we can get rid of the dm sys over dt, total mass in the system, because it's constant, it's equal to 0, right? So this is actually the equation. Okay, so if we make assumptions. Okay, the first assumption we can make, hey, we'll have a uniform velocity going through the control surfaces. For example, in this case, let's say V1 is uniform velocity through the inlet surfaces, and V2 is also a uniform velocity through the outlet surfaces. Okay, of course, V1 is not equal to V2, doesn't matter. I'm talking about on a control surface inlet, V1 is constant. On the other control surfaces outlet, V2 is constant. Okay, if it's uniform velocity in and out the control surfaces, it become this. Okay, so it become mass flow rate out and the mass flow rate in through the control surfaces. I have the summation here. That means that might be multiple, it could be multiple inlet surfaces and it could be multiple outlet surfaces. Okay. I get rid of the volume integral. I just say, hey, total mass in the control volume. The change of the total mass in the control volume in terms of time, the time rate of change, and it resulted from mass flow rate in and the mass flow rate out, the differences. Okay, so that's the first assumption. If we have a uniform velocity, the integration, the surface integration is gone. Okay, we can replace it by just mass flow rate in and mass flow rate out. Okay, that's good, right? The equation looks better. We'll get rid of the integration sign. But if we can make more assumptions, for example, if we have a problem steady state, right? We mentioned steady state before. Steady state versus unsteady, transient, right? If it's steady state, so in the above equation, d mass in the control volume over dt will be 0. So there's no time rate of change of the total mass in the control volume. It's steady, okay? The total mass in the control volume keep constant. Okay, that's the assumption we can make also if it's a steady state. So the first derivative term is gone. So if the flow is uniform in a steady state, then its equation reduced to this. Because the time derivative is gone, steady state, and the integration is gone, surface integration is gone because of the uniform flow. So it becomes a very simple form. Mass flow rate out minus mass flow rate in equals 0, which means mass flow rate in equals to mass flow rate out, which makes sense, right? For example, on this pipe problems. Okay, is this problem steady state? I think so, because for this portion of pipe, the mass doesn't change. It's always filled with the fluid, right? If you weight the portion of the pipe, it's always the same weight. In other words, the same mass. Mass doesn't change. Okay, so for this problem, it's a steady state problem. Okay, so it is uniform velocity as we said before. Okay, V1 is uniform, it's constant on the inlet cross section. V2 is constant, right? V2 on the outlet cross section. So for this problem, the equation will be mass flow rate in equal to mass flow rate out. Okay, so this equation, right? So your mass flow rate in is rho V1 A1, since it's uniform, right? You don't need integration. Your mass flow rate out is rho V2 A2. Okay, so rho V1 A1 equals to rho V2 A2. Basically, that's the equation. Conservation mass equation for this problem. Okay, so you can calculate V1, V2 due to the cross-section area A1 and A2. Okay, that's the relation eventually. V1 over V2 equals A2 over A1. Okay, if you know the areas, if you know one velocity, either 1 or 2, you should be able to calculate the other velocity. Okay, so this is the conservation of mass. Okay, now let's look at the several examples. Okay, the first example I want to give is example 5.4 in the textbook, page 185. Okay, the problem is like this. It's a tank, has an inlet and has an outlet. Okay, at the inlet, the velocity is 7 meters per second, and the cross-section area of the pipe is 0.0025 meters square. Okay, at the outlet, I mark it 2 here. You have an outlet volumetric flow rate of 0.003 cubic meter per second. Okay, the question. The question is, what is the rate at which water is being stored or removed from the tank? Okay, so what is the rate at which water is being stored or removed from the tank? So what does that mean? What is the rate of that? Okay, if you look at obviously this is the conservation mass problem, right? So you'd better write down the conservation mass equation. But the equation has 3 different forms here, as we mentioned before. Okay, 3 different forms. So which form to use? These are the 3 different forms, right? Okay, so which form to use? So the question you ask yourself, is this problem steady or unsteady? Okay, the answer is it's unsteady, unfortunately, right? Because the control volume is the tank. So in the tank, the mass changes with time. You have an inlet, you have an outlet. It doesn't say the inlet is equal to outlet. So it might accumulate and it might, decrease the water level. So that's exactly the question asked. What is the rate of which water is being stored or removed from tank? That means in the tank, in the control volume, the mass changes. It's not a constant. Okay, so the question is, so the answer for the first question is it's unsteady. Okay, so the next question is this problem uniform or non-uniform inlet and outlet velocity? Okay, the velocity is on the inlet and the outlet, right? So the question is it uniform velocities? Are they uniform velocities? Okay, obviously it gave you a one velocity 7 meters per second here, so it's obviously a uniform velocity. Okay, otherwise it has to give you a function, right? It's a uniform inlet velocity. At the outlet, it gives you a mass flow rate, it gives you a volumetric flow rate. So you don't need a velocity. You already have the flow rate. So the flow rate is already being given. So your mass flow rate is just the rho times q. So it doesn't matter at the outlet. So it's a uniform inlet velocity problem, right? Uniform inlet and outlet, you can say that. So it's unsteady and uniform inlet and outlet. Okay, so which equation we use? We're not going to use the general one because we don't need the integration, surface integration, because it's a uniform velocity. So we are going to use the second equation. It's unsteady, so we have to keep the d over dt terms there, right? Your total mass in the control volume, which is in the tank, changes with time. So this is the equation we are going to use. Okay, that's what I wrote down here. Okay. So come back to the question. What is the rate it talk about? The time rate of change, that's the first term. The time rate of change of total mass in the control volume in the tank. That's what the question is. What is the rate at which water is being stored or removed from the tank? Okay. The rate means the time rate change of the mass. That's the first term. So in this problem, now we write down the equation. We know we are going to find the first term, the value of the first term. Okay, is this positive or negative? If it's positive, that means the water is being stored in the tank. If it's negative, that means the water is being removed from the tank. And what is actually the rate, the value of the rate? So we are going to calculate the first term. So in order to do that, we need to find the second term and the third term, which are the mass flow rates. Okay, we can rewrite the equation into this. The mcv over dt equals to mass flow rate in minus mass flow rate out. We move the both mass flow rate into the right hand side of the equation. We get rid of the summation because there's only one inlet and one outlet. Okay, so we reduce the equation into this. So next step is to calculate the mass flow rate inlet and the mass flow rate outlet. Okay, inlet equals rho v1 a1, it's given. Outlet mass flow rate is rho q, it's all given. So then we do a calculation. Turn out to be the time rate of change of mass in this tank is 14.5 kilogram per second. So every second is 14.5 kilogram of water being stored in the tank. It's a positive, that means it's being stored in the tank. Okay, so that answers the question. Okay, so this is our first example.